Year 12. Welcome to moving on into the next area of organic chemistry. Title is up there. You're going to need the title Nucleophilic Substitution Reactions. It's a note-taking video. Stop and start. Make sure you keep up. Nucleophiles. Now, there's the three things that make up how you classify things as nucleophiles. They're going to have lots of electrons. Usually you find those as lone pairs. And the result is that because they're negative, they are attracted, electrostatic attraction, towards things that are positive in some way. Can be completely positive or partially positive, with the electronegativity causing a delta negative and a delta positive. We'll do an example of that. Halogenoalkanes is the probably the most common example at A level. There's a halogenoalkane, bromoethane. When you look at that, I call them halogenoalkanes. Some people call them haloalkanes, depends on your A level course. So when you look at that, there is a charge separation along the CBr bond, causing the molecule to be polar as well, but it's not a polar molecule that matters, it's just the bond having a polarity along its length that matters. Now, there are a whole load of nucleophiles, many of which I can't even name, but at A level there are 4 that you need to know fully about. Most important one, hydroxide ion. But these 3 also strongly feature in A-level chemistry questions. So the 4 nucleophiles, you'll recognise what these 2 are. That is a cyanide ion, not something neither you nor I want to be doing any chemistry with. It's horrendously bad for your body and very toxic, and all sorts of things go on with warnings and hazard signs when you're using that. But hydroxide ions, very much the driving force for today's video. And H2O, NH3 and Cn, but Cn minus. Okay, what goes on is that is attracted to there and it kicks that out. Now, I'm not going to do all of the mechanism stuff because there's a whole collection of things to do with the mechanism. That's another video, that's a different video, but the reaction is termed, because we're talking about nucleophiles, it's nucleophilic. And one thing in, one thing out. Substitution. Don't get it mixed up with free radical substitution. Mechanisms are very different, process is very different, and the outcome is very different as well. Now I'm going to get the board ready for the next bit and I'll see you in a moment. Okay, we're going to go through the reactions of those 4 nucleophiles. But before we do that, because this word crops up in all of those contexts, the word reflux. Now, reflux is a method for carrying out a number of reactions. In the case of what we are doing, it's a very common way. And it's a particular setup of what is called ground glass joint glassware. People call it quick fit, that's its trade name. Other brands are available. It has an upright condenser, the condenser with the cold water flowing around the outside. Normally you would have seen it before in distillation, where it points downhill and distillate drips out the bottom. In reflux, you flip it the other way and you put it upright, and you apply heat at the bottom so that the flask with your reaction mixture in boils, but the condenser stops it escaping by bringing it back down, and it drips back down into the reaction flask, which is often a pear-shaped flask, but it can be a round-shaped flask. And you must have it open to the air, otherwise you'll get a pressure build-up and things will pop off, and that's not good. You don't want things escaping because of that. You don't want explosive reflux. whilst I've been talking, you should have seen the video have a image of reflux, because I certainly wasn't going to be drawing it on the board. Whether you've actually carried that out or not at this point, don't know. But it is important that you can draw the equipment required for reflux, because that is one of the things you can get in a question with a big empty space for you to put the diagram in. So you need to be aware of the word reflux. Now the word reflux is assumed as a set of knowledge if you use the word. It's only when the question says draw the equipment for reflux or describe how reflux works. It keeps the reaction mixture at a boiling temperature that it has. It has a boiling temperature. That makes the reaction go as fast as you can get it to go, because it's heated up. Reactions go faster when they're hotter. But none of the chemicals can escape. And that's the critical thing about reflux, is that it's as hot as you can get it, for as fast as you can get it, but without losing anything. We're going to get on to the reactions, but I'll need to get that on the board, and I'll see you in just a moment. You're going to need to write all of this down. This is how to do the 4 nucleophiles in the actual reactions. I said to you the word reflux will appear. It appears 3 times. So, very much the most common one is hydroxide. Source of hydroxide, sodium hydroxide or potassium hydroxide. Refluxed, and it's in a 50-50 water ethanol solvent mix. The reason for that is that often the halogenoalkane that I'm going to be talking about a little bit later doesn't dissolve in water. So you put the ethanol in to get it to go into solution, and the water dissolves the alkali, the hydroxide contained in whichever one of those you're using. What do you make? Alcohols. Water, it's a pretty slow reaction, but there is a mechanism you need to know, and therefore a reaction that you need to know related to that. You reflux it, it takes ages, unless you've got something else that makes it speed it up, which is the choice of halogenoalkane, which we'll come to a little bit later in this video. And again, it makes alcohols. Now you might think, oh, aren't they the same? Well, there's a subtle difference between water and hydroxides in the way the actual reaction's mechanism works that you need to know. Not in this video, in the mechanisms video. Cyanide ions. Again, something you don't want to be doing. I've never used cyanide ever in my entire time as a chemist, but sodium cyanide, and it dissolve it in ethanol, because it dissolves in ethanol, saves you bothering with the water. In fact, you don't want water, because if you use water you end up doing this one and this one instead of the one you're trying to do. What do you make? Things called nitriles. They contain CN group. You'll see all that in a moment. And ammonia. Ammonia is the only one that's different, because ammonia at room temperature naturally is a gas. If you refluxed it, it would come out of the liquid that is in the reflux, and it would just leave the top, because it wouldn't cool down enough to be condensed. So you can't reflux with ammonia, because you don't want to be A, losing your ammonia, B, it's not good for you to come into contact with large amounts of ammonia. So it's done slightly differently. You seal the container up, it's often done in a tube, and concentrated ammonia solution, so there's plenty of ammonia, and like I said there, stops you losing the ammonia. So it's the only one that's not strictly a reflux, and it makes amines. Right, we're going to go and we're going to do some actual examples, well, a set of examples. I'll see you in a moment. Okay, so you are going to need to write this down, which means you're probably going to have to stop me in order to do it. Stop me at some point, but you're going to need to listen to what I've got to say as well. So this is a set of reactions for, I've put in the middle 1 bromopropane. 1-bromopropane being an example of a halogenoalkane or haloalkane. And here are the 4 reactions that we've just been talking about. So OH minus, it says AQ there. I did say to you it's a 50-50 ethanol water mix, but the OH is dissolved in the water really. Reflux it and you get that. And you get propan-1-ol. Water, same chemical. Now, when you look at that, that's obviously replacing the Br. Here, you've lost a hydrogen. That's the subtle difference in the mechanism that's in the mechanism video, is how do you get rid of the 1 extra hydrogen. And it's the same process here, because NH3 needs to lose a hydrogen in order to be NH2. To make propane-1-amine. Here, now here's a really interesting reaction that you've done. What you've done is you've taken a 3-carbon compound and turned it into a 4-carbon compound, because this carbon is now introduced into the structure. So you have grown the number of carbons by 1. Quite difficult to do. It's easy to join large lumps of carbons together with other reactions, not these reactions. But to grow it by 1. And the reason this is quite good is that it's quite easy to turn this nitrile group, which is a C triple bond N group, you can turn it into other functional groups that you can then go on and carry on your reactions with. It's actually quite easy to turn it into a carboxylic acid, which is very useful for going on to other things. You just boil it with dilute hydrochloric acid. But this, because it's now got 4 carbons, we're going to call that butane nitrile. Technically it's butane 1-nitrile because it's on here, because you could have it joined on in a different place. So we could have a 1 inserted in the name there. But the thing that people forget is that when you name this carbon counts in the length of the carbon chain, so it's now 4 carbons long, hence it becomes butane. This is the growing of the carbon chain. I'm not going to do any more examples because that's it. You need to be able to apply this to whichever compound you're given. So there'll be some questions to practice on with that. But the process, well, not the process, I'm probably doing a process, aren't we? But the replacement, the substitution, is going to be the same each time. Wherever the Br was, the functional group changes to whichever one is the appropriate functional group for your reagents that you are reacting here. And we are focusing on halogenoalkanes. You can do a whole set of substitutions with alcohols, still nucleophilic substitution because the CO bond is polarised. Not for today. I'll see you in a moment because there's some other important content that you need to be aware of. Okay, so we're going to, this last bit is a really important, well, it's a really important part because they ask questions about it a lot. So it's the rate differences that you get when you do nucleophilic substitutions with a range of different organic compounds. That can be different halogens or what it says down there. We'll come to that in a second. I mean, first is how you do the actual practical. The practical uses warm silver nitrate. It's kind of a self-indicating reaction because of that. So warm silver nitrate, you kick out the halogen, it detects that you've kicked it out because, and you notice the solvent is that same thing to make sure the halogenoalkane dissolves as you put some ethanol in there with it. It doesn't say 50-50 because it probably is a bit more random than that. So you get this visible precipitate. Now these shouldn't be unfamiliar to you because they are in GCSE as tests for halide ions, because when you throw the halogen out of the organic compound, it comes out as a halide ion, and you test the halide ion using the silver nitrate solution. So that there will tell you whether you've kicked out iodide, bromide or chloride. That colour detection thing. Got to remember that. It's part of the A-level course as well. The other thing is primary, secondary and tertiary. Now, you may not be familiar with primary, secondary and tertiary, but it's a count of how many carbons are attached to the carbon. So here's the carbon that the bromine is attached to. How many carbons are attached to it? 1. Primary. Here's the carbon that the bromine is attached to. How many carbons is it attached to? 2. Secondary. Here's the carbon again. This one's attached to 3. It makes it tertiary. The chains don't have to be just 1 carbon long. They could be multiple carbons in length. It would still be tertiary in that case. That could be longer, could be off centre. So you need to be able to identify primary, secondary and tertiary. So you look at the carbon where the halogen is and go, how many carbons are attached to that carbon? Simple as that. Just need to do the actual rate differences and then we're done. I'll see you in a moment. So the last bit, what are the actual rate differences? So change the halogen. Iodo reactions are the quickest. Chloro reactions take days. These are done in seconds. These take minutes. These take days. Often you throw the chloro away and it's not shown any sign of doing the reaction. So you would get the precipitate very quickly with the silver nitrate with iodine. You get the pale yellow precipitate very quickly. The cream coloured precipitate appears within a minute or 2. And the chloro probably won't appear at all. You'll throw it away without it ever having produced a precipitate. The cause behind the difference of rates is that it's all to do with the strength of the bond. The Ci bond is the weakest. The CCl bond is the strongest in terms of bond energy. It's not to do with the polarity of the bond. You sometimes get a question where it asks you to compare the differences and establish the reason behind it, or state or explain the reason behind it. En is electronegativity. So the polarity and electronegativity, because this is the highest electronegativity, is not the reason. It's the least electronegative that is fastest. So it must be to do with something other than electronegativity. It's the bond strength. Once you get to the primary, secondary, tertiary, the positional thing, tertiary is almost instant. Literally. Get it all ready, put the last chemical in. 1 second less even, probably, it's done. Secondary, a little bit slower. Primary, slower again, but they do usually work if you're testing it with bromine or you're testing it with a bromo compound or an iodo compound, but not chloro. The cause is not that straightforward. It's to do with how many alkyl groups. Now, alkyl groups are the CH3, CH2 groups that are attached to that central, or that carbon, not central necessarily, but the carbon with the halogen. So they push electrons at the carbon. Right? So they push electrons at that carbon. So if you were to have a carbon with, let's do a tertiary, they push electrons at it, and that CX bond, therefore, the dipole is made even bigger, and therefore the bond is made weaker, and it breaks easier. So if you've only got 2 CH3 groups, it's not as strong an effect, and you've only got 1 CH3 group, it's less of an effect again. So you get a weakening of the halogen to carbon bond. And that's it, really. May need to review the entire video. We are needing to do the mechanisms of these. There's a mechanisms video to follow this one. that explains how the nucleophilic substitutions work and how they are different for, firstly, tertiary. The mechanism is different to primary. Secondary is irritating because it does the mechanism for tertiary and primary in a sort of both of the mechanisms take place at the same time. You need to have the mechanism difference for water and OH. How does NH3 lose the extra hydrogen? All of that stuff is explained in the other video. And that's kind of it, really. Thank you for watching, and I'll see you soon. Goodbye.